Hello everyone, welcome back to Math with Allison. Today we're going to do another exam, so this is going to be on the back end of derivatives. So this is going to be like the first and second derivative test, optimization, linear approximation, stuff like that. So let's go ahead and dive into it. This is an exam from a professor who I've worked with, so this is actually given to students right now as practice for their upcoming exam. So we are just going to go ahead and go through it. This one has 11 questions. I do think it's a little bit tougher than the previous one that I just put up, but we're going to go through it. So problem number one, we're going to use the graph to identify the local and absolute min and max. First, we want to identify the absolute maximum. So that is going to be the largest value that our function reaches, which we can see is going to be right here. So this tells us our corresponding x value is going to be a. Now, for the absolute minimum, it's going to be the same idea. It's going to be the lowest value that our function hits, and as we can see, it's going to be right here at b. So here we have our absolute max and min. Let's go ahead and talk about our local max and min. In order to be a local maximum or local minimum, it has to change from increasing to decreasing or from decreasing to increasing. So if we look at our points, we have a local maximum right here at C, and that's because our function changes from increasing to decreasing. And then when we want to look for a local minimum, we want to see where our function changes from decreasing to increasing. So that's going to be here at B, but it's also going to be right here at D, right? Because we change from decreasing to increasing. So that would be our solution for the first problem. Okay, so here we have the polynomial, and we first want to find the critical points of f. So in order to do that, we need to find our first derivative. And we want to set that first derivative equal to 0. So this is the points where a function is neither increasing or decreasing, which is why it's called a critical point. So here we have our critical point. And then part B wants us to find the absolute extremes on the interval. And remember, our interval is going to be right here from 0 to 2. So first, I'm just going to go ahead and set up our number line. So we want to plug in points to our first derivative, and whether it's positive or negative, that tells us if our actual function is increasing or decreasing. So here we want to see if 3/2 is going to be a local minimum or a local maximum. So I'm just going to go ahead and choose some points in our interval. And if you wanted, you could actually choose the endpoints because these are kind of nice numbers to put in. But if you don't like that, we can plug in, let's do maybe 1, and I am going to do 2. I don't want to choose a number between 3/2 and 2. So let's go ahead and plug those into our first derivative. Alrighty, so when I plugged in 1, I got a negative value, which tells us that our function is going to go decreasing. And then when I plugged in 2, I got a positive value, which tells us our function is going to be increasing. So right here, I can see that 3/2 is going to be a local minimum. And it's actually going to be an absolute minimum because our function is doing something like this. So let's go ahead and plug in 3/2 in order to see what that absolute minimum value actually is. So here we have an absolute minimum at 3/2 comma 0. So I'll go ahead and write that in. So now we need to find the absolute maximum, and that's going to occur either at 0 or 2. So we need to plug both of those into our function and see which one's larger. Okay, so between these two values, I can see that 9 is going to be our largest value. So we have an absolute maximum occurring at 0 comma 9. And so this right here would be our solution. Problem 3, we have the function x times the natural log of x. We want to go ahead and find the critical point. So we're going to do the same process, but in this case, we're going to have to set a product rule. So we have our first term is x, and then our second term is natural log of x. So I'm going to go ahead and set that up. Okay, so the derivative of x is just going to be 1, and the derivative of natural log of x is going to be 1 over x. So let's go ahead and find g prime of x, and this is going to take the cross product, so 1 times the natural log of x, and we're going to add on the other cross product, so that's just x times 1 over x. We could simplify that down a little bit, natural log of x plus 1. And now in order to find the critical values, we're going to go ahead and set this equal to 0. So we get the natural log of x is equal to negative 1. So in order to get x all by itself, I'm going to have both of these raised to e. So here we get these cancel out and we get x is equal to e to the power of negative 1, or if you wanted, you can rewrite that as 1 over e. And this right here is going to be our critical value. Now we want to find the intervals where g is increasing or decreasing. So here we're going to have a hard cutoff at 0 because we can't do the natural log of a negative value. So let's plug in our critical value. So we want to take test points and plug them into our first derivative to see what our actual function is doing. So first we can go ahead and plug in, let's do 1 over e squared. And then over here we can just do value 1. I'll go ahead and plug those in. Okay, so when I plugged in 1 over e squared, I got a negative value, which tells us our function is going to be decreasing. And then when I plugged in 1, I got a positive value, which tells us our function is increasing. So if I were to write this out all officially, we have, and there we have our solution. So now for part B, that should be part C. Use the first derivative test to determine whether each critical point is a local minimum, local maximum, or neither. And so looking at our first derivative test, which we already did, we can see that 1 over e is going to be a local minimum. So this is a lazy way I write out the solution. We have x equals 1 over e as a local minimum because this first derivative changes from negative to positive at that value. So it depends on your teacher or professor what you can write. I know this would be fine for us, so just make sure you pay attention to what's required of you. Okay, so we got a theme going on here. We have a polynomial, and we want to go ahead and find the critical points. So let's go ahead and take the first derivative. F prime of x is going to be equal to 8x minus 4. Set that equal to 0. We get 8x is equal to 4. Divide both sides by 8, and we get a half. And that is our critical point. And now we want to find the interval on which f is concave up or down, which actually concavity has to do with the second derivative. So let's go ahead and find the second derivative. We get f double prime of x is just equal to 8, which tells us it's going to be positive on the entire interval, aka it's going to be concave up on the entire interval. So because it's a polynomial, right, we have a polynomial with a positive leading coefficient, which tells us that the concavity is going to be up. So that checks out, right? Okay, part C, we're going to use the second derivative test to determine whether each critical point is a local maximum, local minimum, or neither. So think about our concavity. If we have a function that's concave up, that means right here we're going to have a minimum. And it's actually going to be an absolute minimum, right? So it's not asking for that, so we don't need to worry about it. And we have that. And we have the reasoning is because it's concave up, right? Okay, so here we're given the graph of the first derivative, and our first thing is to show what intervals that f is increasing. So since this is the first derivative test, we need to pay attention to where it's positive or negative. When it's increasing, that's where our first derivative is greater than 0. So I'm going to look for where our function is above the x-axis. So this is going to be from negative infinity all the way to negative 2. And then our function's never above the x-axis again, which tells us this is the only interval that it's increasing. So now we want to find for what values of x does our function have a local minimum or maximum. And that's going to be where our function changes from positive to negative or negative to positive. So let's go ahead and take a look at where we hit the x-axis. That's going to be right here at negative 2 and right here at 1. So notice here at negative 2, we change from positive to negative, which tells us our function is doing something like this, which means we're going to have a local maximum. So x equals negative 2. Okay, so now let's look at 1, because this is another point where we hit the x-axis, but notice our function is negative and is still negative on the other side. That means our function does something like this, where it's decreasing, goes flat, and then continues decreasing. This is neither a local min or max, so actually we don't need to include that one. Okay, so here we have on what intervals is the function concave upward and concave downward. So when we talk about concavity, we want to look at the rate of change of our first derivative. And so let's go ahead and look at the intervals where our first derivative is increasing and decreasing. So here we have our first derivative is decreasing, and then we switch to increasing right here, and then we again are decreasing. So this has to do with the concavity, right? When our first derivative is decreasing, that means our function is concave down. When our first derivative is increasing, that means we are concave up. So I'll go ahead and write that out. Remember that derivatives are the rate of change. So this function is our first derivative, and it represents the rate of change of the function. Okay, finally, we have the x-coordinates that are inflection points of f, and that's going to be kind of weird. You kind of looked at that, and it's going to be where a function changes from increasing to decreasing or vice versa. And actually, we kind of already included that in our part C. So right here, we have x equals -1, and we also have x equals +1. And that's all we would have to do for this problem. Okay, so we want to find positive numbers, x and y, satisfying x times y equals 24, and such that 3x plus y is as small as possible. So we are trying to minimize 3x plus y. And we have a constraint right here where x times y have to equal 24. So let s equals 3x plus y. What is the objective function in terms of one number x or one variable? So here I'm going to go ahead and use the constraint. I have x, y is equal to 24, and I want to go ahead and solve for y. So here I'm going to divide both sides by x, and I get 24 divided by x. Now let's go ahead and plug in. We found what y is equal to, and we can replace that in our objective function. So here we get s is equal to 3x plus 24 divided by x. If you wanted to, you can rewrite this s equals 3x plus 24x to the power of -1. So part 2, what is the interval of interest of the objective function? That has to do with this part right here where it says we're working with positive numbers. So we have from 0 to infinity. Okay, and so now we want to go ahead and find the two numbers. So this is an optimization problem, and we want to go ahead and try to minimize or find the minimum of our objective function. So I'm going to go ahead and find the first derivative, and here we get 3 minus 24x to the power -2, or you can rewrite this as 3 minus 24 over x squared. So like I said, we're just doing the first derivative test. I'm going to go ahead and set this equal to 0 and solve for x. Whenever you're feeling like, oh, I don't know how to solve for x, just move it out of the denominator. I'm just going to multiply it over. So that's how I would get it out of the denominator. Then I divide by 3, and then we can take the square root of both sides. So here I get x is equal to 2 root 2. Notice I do not care about the negative one, and that's because our interval of interest is all positive numbers, so I don't care about the negative one. So I'm going to go ahead and erase this and move it up. So here we have our critical value, and now we want to go ahead and do the test. So let's set up our number line. We're not going to go less than 0, so I don't care about including that in our interval. And here we have our critical value of 2 root 2. We want to plug values into our first derivative, s prime, because that's going to tell us if our function is increasing or decreasing. So let's go ahead and take test values. I'm going to choose 1, and then 2 root 2, I think we can go ahead and choose 4. If you're not confident about that, if you're thinking, oh, I don't know how to find 2 root 2, the root 2 is less than 2. 2 root 2 is going to be less than 2 times 2, which is equal to 4. So I'll go ahead and plug those into our first derivative. Okay, so notice here when I plugged in 1, I got a negative value, which tells us our function is going to be decreasing. And then when I plugged in 4, I got a positive value, which tells us our function is going to be increasing. So here we found that we for sure have a minimum. And that is exactly what we want to do because we wanted to make 3x plus y as small as possible. So now that we know it's a minimum, we have our x value, and we want to go ahead and find the corresponding y value. So if we remember, we solved for y, and that was equal to 24 divided by x. So now I can plug that in, and we have 24 divided by 2 root 2. If you wanted, you can simplify that to 12 over root 2. In our case, you wouldn't have to, but again, it depends on your teacher. And then we have our coordinates. And that right there is our final solution. Okay, so here we want to write the equation of the line that represents the linear approximation of our function at the point a equals 1. So when we want to do this, we are trying to solve the equation y minus y1 equals the slope times x minus x1. We already have our x1, and this is going to be the value of 1. So let's go ahead and find our y1. We're going to do that by plugging in our value into the function. Okay, so now we have our y1, and the last step is to find the slope. The slope is going to be by finding the derivative and plugging in that x value. So let's go ahead and find the derivative. I'm going to actually do something kind of sneaky here. If you wanted to do quotient rule, you totally could. Or you could rewrite the function as 2 times 2 plus x to the power of -1. I bring down that power, so I get -2, 2 plus x to the -2, and I would multiply by the inside, but the derivative of the inside is just 1. So if you wanted, you could rewrite this as -2 over 2 plus x to the power of 2. So now let's go ahead and find the slope of our tangent line. So we have m is equal to f prime at 1, which is equal to -2 divided by 2 plus 1 squared. And this is going to be what, -2 over 9? And so here we have our slope. So now we have all the parts that we need for our entire equation. So let's go ahead and plug that into our equation for our line. I'm going to go ahead and get y all by itself. And there we have the equation. So now we're going to go ahead and use this approximation to estimate the value of 0.9. So that means I'm just going to plug in x is equal to 0.9. So I wouldn't suggest leaving it like this. This is technically correct, but I think that given the context, we want to try to simplify it as much as we can. So here we get negative 0.1. And I'm going to rewrite that as negative 1/10 because I think that helps us simplify it down. So here we can divide this one out and that becomes a 5. And actually the negatives cancel each other out. So here we get y is equal to 1 over 45 plus 2/3. That's getting pretty close. I mean, I would say that's okay, but I'm going to take it a step further. I'm going to go and multiply this by 15 over 15 to create a common denominator. So I get y equals 1 over 45 plus 30 over 45, and that is going to be equal to 31 over 45, and that is our final solution. That's definitely the safest bet, but if you're stressed about time, then maybe you can move on and come back to it if you have time and keep simplifying. Up to you. Okay, here we got the mean value theorem, and they actually give the definition here. And so we want to go ahead and take this function right here, and we want to determine if it satisfies the condition of the mean value theorem. And then if so, we want to find the points guaranteed to exist by the theorem. So let's go ahead and take the first derivative. I'm going to rewrite the function as x plus x to the power of negative 1. So here we can find the first derivative, which is equal to 1 minus x to the negative 2, or 1 minus 1 over x squared. So we want to go ahead and make sure that it's differentiable on this interval, aka there are no illegal values. In our case, it satisfies that part, and we also want to make sure that it is continuous on that interval. So that means our actual function has no illegal values on this interval. And again, no illegal values. Our only illegal value would be 0, but 0 is not included in the interval. So here we want to say okay, so now that we have that it satisfies the condition, let's go ahead and actually solve. First, what we can do is this whole part, I don't know what to call it. So let's go ahead and plug in our value. So f of 3 is going to be equal to 3 plus 1/3. And then f of 1 is going to be equal to 1 plus 1, which is equal to 2. So let's go ahead and set it up. We have f of 3 minus f of 1, all divided by 3 minus 1, which this is going to be 3 plus 1/3 minus 2, Allison, divided by 2. We get 3 minus 2 is equal to 1 plus 1/3 divided by 2. That's equal to 4/3 divided by 2. And if you wanted to think about this, that's also just 4/3 divided by 2 over 1, which means we can flip it and multiply by the reciprocal. And we can see here these 2's cancel out, and we get 2/3. So I'm going to go ahead and erase all of this so I have more room. Okay, and remember, this is equal to the first derivative. And we want to go ahead and solve for x. So let's go ahead and subtract 1 from both sides. We get negative 1/3 is equal to negative 1 over x squared, and we can cross multiply. Here the negatives cancel out. We get x squared is equal to 3, so we want to take the square root of both sides, and we get x is equal to the square root of 3. Notice I did not include the negative 1, and that is because we are working in the interval 1 to 3, and that negative value is not going to be included in there. So here we get our solution that satisfies the mean value theorem. Woohoo! Okay, we got some limits in here. Let's go ahead and try these out. Our first step with limits is always to try direct substitution first, so let's go ahead and plug in that value of 1. So here we have indeterminate form, which means we can use L'Hopital's rule. If you wanted, and I just noticed this is actually a difference of cubes, and if you remember those formulas, you can go ahead and set it up. But if you don't recognize that or remember it, like me, I don't remember it right now, then we can go ahead and just use L'Hopital's. So I'm going to take the derivative of the numerator, and I get 3x squared divided by the derivative of the denominator, which is 1. So really, this is just the limit as x approaches 1 of 3x squared, and we can go ahead and use direct substitution again. So let's plug in that value of 1, and we get 3 to the power of 1 squared, which is just equal to 3. And so this right here is our limit value. Let's go ahead and try another one, and of course we're going to try direct substitution first. Let's plug in that value of infinity. Remember that infinity is just a concept here, and so technically this is kind of weird to write out, and some people don't like it, but don't be mad at me because we're just trying to see the indeterminate form, which we just found right here. So this goes to infinity over infinity. So what we want to go ahead and do is use L'Hopital's. So here we get e to the x because that doesn't change, divided by 2x. And if we use direct substitution, we have the numerator is again approaching infinity, and the denominator is also approaching infinity. So we have another indeterminate form, and so here we can apply L'Hopital's again. And if we agree, when we use direct substitution, this is just going to be infinity, right? Because e to the infinity is infinity. Infinity divided by 2 is infinity. So there we have our solution. Okay, so let's try direct substitution. We have x is approaching pi over 2. So we get sine of pi over 2 divided by pi over 2. And so this actually goes to 1 over pi over 2, which is equal to 2 over pi. We just flipped that fraction. So this one was a tricky one. I'm sure it was there to make you think, wait, did I do something wrong? You did not do something wrong. This right here is our final solution. Okay, so now we're going to evaluate the limit again. So here we have the limit as x approaches 0 from the right side of this function. So if we were to try direct substitution, we would get that this right here is approaching 0, and this right here is approaching negative infinity. So this gives us 0 times negative infinity, which is illegal. We cannot do that. So, but we also cannot apply L'Hopital's because in order to apply L'Hopital's, this has to be a quotient. So we need to make this look like a fraction. And I'm going to show you a trick here. I'm going to rewrite this. We can move one of these to the denominator, and we do so by making the exponent negative. And so now what I'm going to go ahead and do is rewrite that. So we get the limit as x approaches 0 from the right side, natural log of x in the numerator, and 1 over the square root of x, or to the power of 1/2, whichever you like. So now let's go ahead and use direct substitution. We have that the numerator is still approaching negative infinity, but now notice on the denominator, 1 divided by a very small number goes off to infinity. Since we're approaching 0 from the right, it's going to be positive infinity. And so this is approaching negative infinity divided by infinity, which tells us we can go ahead and use L'Hopital's rule. So this was a very roundabout way of getting there, but I'm going to go ahead and use this one because I think it's the easiest to take the derivative of. So I'm going to go ahead and write that. So in the numerator, we get 1 over x. In the denominator, we get negative 1/2 x to the negative 3/2. So lots of fraction action going on. Let's go over here and try to simplify that out. So we have 1 over x divided by negative 1/2 x to the negative 3/2. I'm going to rewrite that as 1 over x divided by negative 1 over 2x to the 3/2. This tells us that we get to multiply it by the reciprocal. So we get 2x to the power of 3/2 divided by negative 1. And now notice here, this whole x cancels with one of the wholes here, so we get 1/2. So really what this simplifies to is 2x to the power of 1/2 divided by negative 1, or negative 2 times the square root of x. So I'm going to go ahead and replace that. And when we use direct substitution here and we plug in 0, we just get 0 because negative 2 times the square root of 0 is 0. And that right there is our final solution. I think this one might be the most difficult one on the exam. Lots of tricks in there. But when you think about it, if you're stressed out about it, this one's only 4 points, so you're potentially only losing 4. Okay, let's go ahead and try this one. I'm going to give you guys a hint. Whenever you see a variable in the exponent, we're going to use natural log. So what I'm going to do is I'm going to say, okay, I'm going to set y equal to this. That way I can take natural log of both sides. So the purpose of doing that is that it brings the exponent down. Okay, so just like last time, if we tried direct substitution, we would have this going to 0 and this going to negative infinity, which tells us we have indeterminate form, but it's not the form that we can take L'Hopital's of. So again, we need to make this a fraction, and I'm going to do it using the same trick. So that's the trick I used. I brought the exponent down, and then I rewrote it as a fraction. So now let's see what this is approaching. We have this is approaching negative infinity, and this is approaching positive infinity. So we have a indeterminate form, which tells us we can use L'Hopital's. So that becomes 7 divided by x. And then instead of 1 over x, I'm going to think about it as x to the negative 1. So we get negative 1x to the negative 2. So again, lots of fraction action going on. Let's go ahead and simplify it over here. So 7 divided by x divided by negative 1x to the negative 2. Let's go ahead and rewrite that as negative 1 over x squared. So then we can go ahead and multiply by the reciprocal. So here we can notice that one of the x's cancels out. And so what we're left with is 7x divided by negative 1 or negative 7x. So let's go ahead and replace that in our thing. And now we can plug in our limit value. So here we get the natural log of y is equal to 0. And I'm going to go ahead and bring it over here because what we want to do is have both sides raised to the power of e. So that way these natural logs cancel out and we get y is equal to e to the 0, which is equal to 1. And that right there is our final solution. One more problem. So here we're going to determine if it's true or false, and we're going to give an explanation or a counterexample. So when a linear approximation is used to estimate the values of natural log of x near x equals e, the approximations are overestimates of the true values. So if you're like me, we enjoy a visual. So I'm going to go ahead and draw out the natural log of x. That's pretty good. Okay, so here we were thinking about x equals e, so I'm just going to go ahead and pretend that e is right here. If I were to find the linear approximation at that line, it would just be the tangent line. So the tangent line would look something like this. Okay, that's pretty good. So let's go ahead and think about if it's an over approximation or under approximation. We have, let's say I was approximating this value right here using that line. I would have the actual value is down here and our approximation is up here. And so this would be true. It is overestimates. So I would say our visual is a good explanation. If you wanted to write out why, you could. If you're thinking, oh my gosh, I'm not going to remember what the function of natural log of x looks like, then you can think about the concavity. So what we would have to do is find the first and second derivative. So let's go ahead and set that up. Okay, so let's go ahead and find the concavity. And if you guessed it, it's always going to be negative because let's just take 1 for example. No matter what number we plug in, we're going to have a negative value, which tells us it's going to be concave down. So since it's concave down and you just go ahead and choose any linear approximation line right here, we have the exact same reason why it would be an over approximation. And that's because this right here is our actual value. This right here is the estimation. So if you don't remember what natural log looks like, you can just find the concavity of the function. So that's all I have for us today. If you enjoyed this video, I have many more like it, so make sure to check out my playlist. They're linked down below. Otherwise, if you're studying, I wish you luck on your exam. And please give this video a thumbs up and comment other problems or topics you'd like to see done. Thanks for watching.